Hi, so I'm Caroline, and I was supposed to do this presentation with Crystal, but unfortunately I caught COVID, so here we are. This presentation is about an article that claims to have found where Earth's missing argon is. So a few things about argon and how we know it's missing. Argon is the negative beta decay product of potassium 40. So when potassium 40 loses an electron, it becomes argon. And this process happens over 1.25 billion years. The half-life is the amount of time it takes for an initial amount of a radioactive isotope to lose half of its original amount. So all the argon on Earth is product of this potassium 40. And something about argon is that it enters the atmosphere after it's been exposed to the surface because it's a noble gas. So when we're talking about missing argon, we're talking about how we have this model, this idea of how much of each element the Earth should in theory have. We actually talked about this idea a few times in class, the bulk silicate Earth model. And we've come up with this through our observations of rocks at the surface to looking at meteorites that could give us insight into what the Earth looks like a bit deeper. So based on that model, we've only accounted for 40 to 60% of the argon that we think we should see. So the missing argon that we're talking about here is the stuff that we can't find. So where is it? People used to think that it was actually the material in the mantle that has never ever reached the surface. But that doesn't really work, because if that's the case, it means that the mantle would be structured in sort of, it would be stratified, it would have layers. And this material that the argon would supposedly be in would be wrapped around the core like a blanket, but that's actually not true for the structure of the mantle. There's a lot of interaction between the upper and lower mantle. We see that with things like mantle plumes, which bring up material from deeper within the mantle. And then we also have subducting plates, which bring new material in. So there's actually a lot of mixing happening. And because of that mixing, we should have already been able to see that argon. Or maybe because potassium is what argon comes from, and we're not seeing enough argon, it means that we've actually overestimated the amount of potassium there is. So this article goes to say then that the missing argon could be found in ancient subducted oceanic crust. So usually potassium is an element that's incompatible with olivine, which would be found in the oceanic crust. But at the time of when these plates were formed, which was a very, very, very long time ago, potassium was able to be in the oceanic plates. So when those plates are subducted, eventually the potassium decays into argon. And the argon is then trapped in the subducted crust, and because it's cooler than surrounding material, it actually sinks right to the bottom of the mantle. So because of this discovery, we're able to better picture the mixing that happens in the mantle. So these discs here, to me, they look like CDs. Towards the middle of the CD there, that's it's deeper in the mantle. And the outside rim there would be the crust. So we can see the mixing that happens actually because of subducted oceanic crust. So when the oceanic crust is subducted, it actually pushes material in the mantle back up. Think of it like if you're sitting in a bathtub and then you get in and the water level rises. It's the same thing where material is pushed down, so some material is pushed up, and then lots of mixing and melting happens. You can see that some stuff has been melted more than once in figure A. And that stuff actually, according to figure B then, is subducted oceanic crust. So this material has been melted lots and lots of times. C shows where the potassium is, and then of course, because it decays into argon, it's where the argon shows up eventually. So in summary, the missing argon was found in the ancient subducted slabs, and it got there because of the potassium decaying to argon when it's in the mantle. And as a result of this study, it was proven that the mantle is not stratified, and that there's actually a lot of mixing that happens. So thank you for listening to this presentation. It's too bad that I couldn't be there in person, but thank you for teaching a great class, and I hope you have a wonderful day.